Well, luckily in this case, I was listening to your voice.
Yes,
not
it's,
mine.
yeah, it's fine.
So,
All right. So we're going to start looking at the first of the tests that we can use to determine if a series is convergent or divergent. We're going to start off with a test that pretty much always works as long as it meets the certain conditions at the top. It's not always necessarily the easiest way to do it. There are ways that are a little bit easier to do convergent and divergent, and we will look at those next. But this is one of those ones that's like the fallback one. It's like if you can't think of any other option to use, try the integral test. So the question is why would the integral test work? So what does an integral find you?
Area
Nope,
under
that's
the
not the
curve.
integral. Yes.
The area
Yeah, so it's finding you the area under the curve, right? Okay, so now if I have a series, what is a series giving me?
times where they meet up.
No. Still not the right answer. What does a series find? So what does a series do? Yeah.
It finds you the sum of
Okay. When you first learned integration back in Calc 1, how did the teacher show you how to do it? What was the name of it? Starts with an R. Riemann sums.
Yeah.
So you did it by literally finding rectangles under a curve. And they were more, and then they were infinitely smaller and smaller and smaller. And so basically it came down to the summation, which was your integral. And that's actually where the symbol for integral is. It's literally an elongated S for summation. So when you're looking at finding the sum of a series, it's in essence the same thing as an integral. It's just the actual bars are units. They're one each one. So they don't get infinitely smaller. They're always staying as one. So the integral test works because if the actual integral converges, if I'm adding up a bunch of stuff that's underneath it anyway, the integral converges. If I'm always underneath it, then whatever underneath it also has to converge. If the integral diverges, if it goes off to infinity, and if I add up all the stuff underneath it, it's also going to diverge. The one main piece, the one big thing that you don't want to do is the integral test is not going to tell you the sum of a series. Okay, because the integral is adding a bunch of extra stuff in there that we don't want. So the integral test is not going to give me the actual value of a series, but it will tell me if it's convergent or divergent. So there are a few certain things that we need to actually look at before we do the integral test. The first thing is it has to be continuous. Okay, so whatever the series or the function that I'm using to represent that series, it has to be continuous. It also always has to be positive. Okay, so continuous, positive. And it has to be decreasing. If the function was increasing, what would be by definition, it would be divergent, right? And that would go back to our test for divergence that we did. If the sum doesn't equal 0, it's divergent. And the only way to get to 0 would be it's decreasing. So if it's not decreasing, we know automatically it's divergent. We don't have to do the integral test to do it. So for the integral test, it has to be continuous, positive, and decreasing. Those are the three things we have to determine before we can do the integral test. A lot of times you're going to be able to look at the function and go, yep, that's continuous. Yep, that's always positive. Yep, it's decreasing. If you can't, just by looking at it, then you're going to have to do some calculations. Continuous, how do we determine if something's continuous? Right. What's the things that would restrict it from keeping going?
Zero.
A zero where?
Explanation.
Nope, that would equal zero.
I think so.
An asymptote, but how do asymptotes form normally?
By, let's say, it's like y minus 4. Y can't ever equal 4.
Only if it's where. This, I know what you're saying, but you're missing one very important piece. Where does that y minus 4 have to be in terms of the function? Right, it has to be in the denominator. I can't divide by 0. So domain restrictions, basically. If I have domain restrictions, that would prevent it from being continuous. So when we're looking at the function, we want it to be continuous over the domain that I'm looking at. Most of your series will start at 1 and go to infinity. So that's where we're looking at that piece. Okay, so we're looking at it going from 1 to infinity. Positive, that's pretty easy to recognize if the function is going to be positive or not. The only ones that will typically fall into the situation where you don't possibly know would be if you have trig functions in there, sines, cosines, stuff like that, that go above and below. If you have an absolute value, that takes care of that problem. If you square it, that also takes care of that problem. So it has to always be positive. It can't jump above and below. How do we determine if a sequence or in this case, the function is decreasing?
Put a bigger number in there, doesn't get smaller.
Okay. That would work, except we have some functions that do crazy things. So you can't test every number. But if a function is decreasing, what is always going to be true?
Converges.
Yes, not that it converges.
You mean decreasing everywhere?
Decreasing everywhere over the domain that I'm looking at. Yes. Remember, derivatives tell you slope. If my slope is negative, that means the function's decreasing. So as long as the function is decreasing over the interval that I'm looking at, so like I said, in most cases, 1 to infinity, but it doesn't have to be. It could be 2 to infinity or 3 to infinity. As long as it is decreasing, the domain or the derivative is negative over that interval, it's decreasing. So sometimes you will have to take the derivative and show that it is negative over that entire area. Okay? If those three things are true, the integral test will work. To do that, all you're going to do is take the integral from 1 to infinity of that function. Now, if that is convergent, which means it goes to a specific value, then my series is also convergent. Okay. Notice it doesn't say it goes to 0 or anything else. It goes to a specific value. That means the series is convergent. Okay. If the integral is divergent, which means it goes to infinity, then the series is divergent. Questions with that? Does that make sense on why this should work? No. All right, here's just a visual representation. If we're looking at all the ones underneath it, get smaller and smaller. Obviously, it's going to converge. Same concept here. If I'm looking at this stuff's all above it, obviously it's going to keep getting more and more, and it's not necessarily going to converge. So just a visual representation of it. All right, so let's look at this one. 1 over n squared plus 1. All right, so we need to check Those three things. Is it continuous?
Yes.
Okay. How do you know?
Because there's a constant at the bottom. Will never be negative or zero at the bottom.
How do you know it's never going to be negative or zero on the bottom?
Where
Okay.
if I put -1 in there,
What if it was that?
then yeah, not a problem.
Okay, so it's not the square that's doing it. So to show this one is continuous, we do n squared. The only thing that would work would be n squared plus 1 in essence equals 0, which is n equals the square root of -1, which doesn't work. So in this case, this is always continuous over that interval. If it was n squared minus 1, it wouldn't be continuous. It wouldn't be continuous at 1, which means we wouldn't be able to do this as is. We would have had to do it from n equals 2 to eliminate that possibility, the 1 over 0 situation. So this is continuous. Good. Next was what? Positive. In this case, there's no negatives in this. And remember, series are always plugging in positive numbers. So a series is always going to go from 1 or 0 up. It is never going to go into the negative values for your n. So whatever values you're plugging in, like you don't have to worry about the negative possibility of those integers. You're only dealing with whole numbers in essence. So this one is positive. We don't really have to actually go through and do anything with that one. Is it decreasing?
Yeah.
How can you tell?
If I take the limit of it, bottom will continuously get bigger.
Yeah, so the bottom's getting bigger, the top's not changing, right? If the bottom's getting bigger and the top's not changing, that's decreasing. So we don't necessarily, so this one we do not have to do the derivative of it to prove that. This one you can look at and figure that case out. If it was like n over n squared plus 1, then you might have to show the derivative because both the top and the bottom is changing. And you'd have to show that the bottom is changing faster than the top is. All right, so we can do the integral test for this one. The very first thing you're going to want to do before you even do the integral test, actually, technically, even before you just did what I just did, always check the test for divergence, okay? Because it's really quick and easy. Does that go to 0?
Yeah.
Yes, okay. So it's not divergent based on the test for divergence. Always check that first because it's really easy to check and it will eliminate a lot of problems for you. Okay, so that is the very first thing you always want to check is the test for divergence. This one, it gives me equals 0, which is inconclusive in the test for divergence. So we're going to do the integral test for this one. So we're now looking for the integral from 1 to infinity of 1 over x squared plus 1. All right, somebody look up the integral of 1 over x squared plus 1 or look on your index card because it's one of the ones that you should like either have written down or be able to look quickly find. It is not one you're going to sit here and calculate out. 1 over x squared plus 1. It ends up being a trig function of some kind.
Tangent.
Yes, it is inverse. So it is the inverse tangent. And we're doing this from 1 to infinity. Now, I will tell you right now that depending on your math teacher, it depends on how you're going to see the infinity written here. Technically, you are not allowed to plug in infinity to anything. because infinity is not a number. Okay? What you're doing when you plug in infinity is you're looking at as that value is going to infinity. So you will typically see this problem written like this. Like that. Okay, because technically it is not, you can't just plug in infinity. Now, I will tell you right now, I'm typically going to write it as the first one. Okay, because in my opinion, you should understand the concept of that the limit is as it's going to infinity, not actually plugging in the infinity. You're going to get the exact same answer out at the end, no matter which way you're different looking at it. The last one is just the more proper way to write it. Okay. All right, so arctan is the it's giving me the values of, so I'm getting the radians when I plug in the value. Remember, it's the opposite. So what value, so in essence, what value of tangent is going to give me an infinite value? So what value of radian does tangent go to infinity? Yes, because if you think about it, which value of tangent, remember, tangent is sine over cosine, right? So you're looking for the value that's going to give me a 0 on the bottom. And 1 over 0 is pi over 2. So this equals pi over 2 minus
The inverse of tangent is still sine over cosine.
well, remember, you're looking at its sine. Well, yeah, and it's not okay. I'm thinking about it backwards because it's going to be easier for you to think about it that way. That's why I said which integral or which radian is going to give me an infinity when I get my answer. Instead of the arctangent of infinity is what radian. If you think about it, it's easier to think the other direction because then you can use your unit circle for it. Like the next question is which value of tangent is going to give me a 1 as the answer. That's where sine and cosine are equal to each other, which is pi over 4. So in this case, this integral goes to pi over 4.
And it goes to pi
So
over
since
4.
the integral goes to a value, it converges to pi over 4. So the function or the series or the original series that I had is convergent. I don't know the answer for it. I just know it's convergent. What does Ben want?
Why does it converge to pi over 4?
The integral?
Yeah,
integral
like
converges to
I
pi.
see the
Okay,
I'm
so
following all the math, but then you do pi over 2 minus pi over
the
4.
series does not.
Okay.
Yes, Ben or no Ben?
So how do you know what the series converges to?
We don't.
No one-
Not at this point.
It's one of those things that, like, if you're asking us if it's convergent or divergent, we don't need to find the answer. We just proved that it's convergent.
Correct. Yeah. Yeah. So there's two different ways that you're going to ask this question. You're going to get asked it as most of the questions are literally going to ask you, is the series convergent or divergent? Okay. We are going to look at a way tonight to be able to figure out an approximate value of the series. If you remember when we talked on the other class, we looked at the geometric series and we were able to find the exact value of a geometric series because we have a formula for that. Most series, we will not have a formula to find the exact values of them. We will be able to approximate them. We'll be able to get them down to a specific a value or whatever else in terms of your, like a calculator type value, but we will not be able to get the exact value. That's why that pi over 4 tells me that this series, the integral converges because it goes to pi over 4. So yes, the area under the curve from 1 over x squared plus 1 all the way to infinity is pi over 4. That is the area under that curve. Okay, which means it's convergent. That doesn't tell me that the series goes to pi over 4. It just tells me that the integral test tells me that the series also is convergent because the series is less than that. Because we're cutting out holes. Like we're not, the bars aren't going all the way up to perfect to that integral. There's going to be holes above it. But since it's lower than the integral, I know that it also has to converge. Okay. All right. Let's get theoretical for a second. All right. So 1 over n to some power. 1 over n squared, 1 over n to the third, 1 over n to the fifth, 1 over to n to anything. That p can be literally anything. Okay, it can be positive, it can be negative, it could be a fraction. It doesn't matter. So if you think about it, 1 over n squared, 1 over n to the third, those are things that could come up a lot. Right? So if we have a way to figure out if that type of thing is convergent based on what p is, that's going to make my life a lot easier. And I'm not always going to have to go back to the integral test and those type of things. So remember I said I'm going to show you a whole bunch of ways that make life easier after not having to do the integral test. This is going to be one of them. So the question is which values of p is this going to be convergent? So if p is less than 0. So let's start with that. So if p is less than 0. That means it's negative, right? And if it's in the denominator and it's negative, that really means what? No. It's going to go to the numerator, right? It just switches spots. So in essence, if p was that, that's the same thing as saying n to the negative p is up top, because it's going to be negative. So p is going to be up there. Now this is no longer a fraction, right?
Increasing.
That's always going to increase, right? It's going to keep getting bigger and bigger and bigger. So this fails, or in essence, is the test for divergence. That doesn't go to 0. Right? I can add up all those numbers no matter what. It's going to get bigger. It's never going to go to 0. So I know p can never be less than 0. Okay. What happens if p equals 0? If p equals 1, or sorry, 0, that's going to be 1, right? So n equals 1 to infinity of 1. If I keep adding a whole bunch of 1s together, is that ever going to hit 0? No. So that's also the test for divergence. And it diverges. Okay, so we've now shown that if it equals 0 or is less than 0, it diverges. So the next one we're going to have to look at is, well, what happens if p is greater than 0? Okay. So if p is greater than 0, that means it's a fraction, correct? Okay. So the question is, so that's still just 1 over n to the p in essence. So we can't use a test for divergence on this because that would go to zero. No matter what the bottom is, eventually it's going to go to zero. So it doesn't fail based on the test for divergence. So we have to do something else. So we have to use our integral test for this. So is it continuous?
Yeah.
Yeah. Okay. Is it positive? Okay. Is it decreasing? Yes. Okay. So we can do the integral test for this one. So I now have the integral from 1 to infinity of 1 over x to the p dx. So how can we figure out if when this is divergent? So let's look at this integral. All right, so how do you want to find this integral? Not you, somebody else. If it was x squared, how would you want to do it? Huh? What did you say? Yeah, absolutely. If I don't have to deal with the fraction, why deal with the fraction? So yes, you'd absolutely bring it to that. You make it x to the -2, and then we could use our power rule, right? So let's do that. So that was absolutely the correct answer. Okay, what's the integral? How would I do the integral for that? What's the integral for power rules? You add 1 and divide by it, right? Okay, so this goes to x to the -p plus 1, right? Over -p plus 1. 1 to infinity. Okay, so I can pull out this 1 over -p plus 1, right? Because that doesn't really matter in terms of the x. So I'm literally just looking at the x to the -p plus 1 from 1 to infinity. All right. Can I now put that back in the bottom? Yeah. If I put this back in the bottom, not p. All right, so now we can plug in our values. If I plug infinity to that, what's that going to? 0, right? Because it's 1 over an insanely large number. If I plug 1 to that, it's going to be 1 over 1, which is 1, right? So I get 1 over -p plus 1 times 1, which is just 1 over -p plus 1. Okay. So that's the answer there. So the question is, when does it converge and when does it diverge? So I have -p plus 1 on the bottom of a fraction. Okay. So if P is, so which value do you think is the most important number in this? Like, if you're going to look at this as a fraction right here, what number would you like to think is a very important number in the case? Still not you.
Separate from that.
Okay.
Wouldn't it be the result of an be minus the result of the one, so shouldn't it be one over one?
Oh yeah, right. That's negative. Yes, that's -1. So you're right. That does switch the values around. Believe it or not, it doesn't change much. Okay, there we go. Still doesn't change my question. It might make it a little easier for you to figure out the number now, though. Huh? 1, right? Because 1 would make the bottom 0. Okay, so 1 seems to be important. If I want my paper, there we go. All right. So if P equals 1, that would be 1 over 0, right? Is 1 over 0 convergent? No. So it's that would be divergent. Okay. If P is greater than 1, it would now be 1 over a number, right? Which would be fine because that would be convergent, correct? Yeah, so if P is greater than 1, it's convergent. So the only other value that we have to look at is between 0, because we already showed that 0, anything lower than 0 is not working, and 1. So if I had a fraction down there, I would have P minus 1 is less than 0, correct? So if we went back up here, if P minus 1 was less than 0, remember this right here, that's P minus 1, correct? If that was less than 0, what happens to that fraction? It's now no longer a fraction, right? So that would not go to 0 anymore. That would go to infinity, correct? So that is also divergent. So what we showed, so where is the only time this is convergent? Right. So if P is greater than 1, it's convergent. If P is less than 1, it's divergent. That's known as the P series. Very important series that makes your life a lot easier. So the P series states 1 over any value to the P power. So it's always going to be n to any power. Doesn't matter what the power is. If that power is greater than 1, it is convergent. If that power is less than or equal to 1, it is divergent. That is known as the P series test.
We can use it on anything.
Yep. As long as
It's the same thing.
it's in that format. And we're going to look at some stuff on Thursday's class with comparison tests and stuff on ways to be able to get things to go down to look like that to make our lives easier. But the only way I could show you that was you needed the integral test to do it. Oh, and by the way, I just did chapter 7, 8 that we skipped back when I did chapter 7. That's what that was that lesson right there. How to do integrals to the infinity. So in the first series, we got 1 over n to the third. What's P? No, end of the 1 over end of the third, P is 3. It's just the power. Since P equals 3, that is greater than 1. Therefore, that's convergent. And the bottom one, the power is 1/3 because it's the third root, right? So since my P is 1/3, that is less than 1. That is divergent. All right. Let's do one more of these. All right, let's look at this one. Not a P series. How do I know it's not a P series? It's not just one n to some power. Yes, there's no P. All right. So how are we going to do this one? Right now, the only other method we have, is it a geometric series? No. So we know it's not a geometric series. It's not a P series. So the only other way that we know how to do things. So let's first check the test for divergence. So the sequence, does that sequence go to 0? Question is, does n get bigger than ln of n?
Yes.
So ln of n tends to tail off, right? That's the whole point of a logarithm. So the n's going to get bigger in the bottom. So yeah, that's going to go to 0. So we kind of can determine that part. All right. So let's use the derivative test. Not derivative, the integral test. So first thing we have to determine is it continuous? Is ln of n, forget the n on the bottom. Is ln of n continuous?
Oh, wait.
Where is it? Where is ln or a log discontinuous? 0. ln of 1 is 1.
File in 1, 0.
Oh, sorry. ln of e is 1. ln of 1 is 0, but 0 is continuous. 0 is an answer. But ln of 0 is negative infinity because I'm bound. So it is discontinuous at 0. It's also discontinuous at 0 because n can't be 0, right? Okay. But I'm starting at n equals 1, so I'm not using the 0 anyway. So we're good with that. Okay? So it's continuous. Is it positive? Is ln always positive? Okay. So when does ln become positive? When it's bigger than 1. 1 is 0, right? Anything after that point is positive. Since we're starting at n equals 1, this is positive. This is why it's not one of those things that you can always just, yep, done. Like, you have to think about some of these things to be able to show some of these things to be able to use the integral test. Because if it doesn't meet those criteria, the integral test is going to give you incorrect information. Okay? So, because n is greater than 1, it is continuous and positive. Is it decreasing?
Yeah, it's going to 0.
Huh? ln increases and n increases, but the question is, does ln of n over n decrease? So this is not one that you can just look at and go, yes, it decreases. Like 1 over n squared, yes, decreases easy, no problem. Anytime you have something on the top and the bottom, you kind of like have to start thinking about it. So how can we show a series is always decreasing? We have to take the derivative of it. So we need the d dx of ln of x over x. I'm really going to test your remembering skills, which I'm not having very much faith in at the moment. What's the quotient rule?
Derivative of first
First
times
times the second minus the first times derivative of the second over the second squared.
Very good. Very good. All right. So if f is ln of x, what's f prime? 1 over x. If g is x, what's g prime? 1. All right. So my derivative of this one is 1 over x times x minus ln of x times 1 over x squared, which is 1 minus ln of x over x squared. Okay. So I need this to be what? Negative, right? Yeah, because I want it to be decreasing, correct? So 1 over x squared has to be less than 0. Can the denominator ever be negative? If the denominator is always positive. So I can ignore the denominator and it's not going to change anything. So I really am just looking at 1 minus ln of x is less than 0. So I have negative ln of x is less than negative 1. Ln of x is now greater than 1. Remember, when you divide by a negative, you switch your inequality signs. How do I get rid of the ln? E. So x is greater than e. Leave me a message. All right, so ln's got to be greater than e. Okay. What's the approximate value of e? 2.718, right? Okay, so is this function always decreasing?
Negative.
It's increasing until it gets to e, right? So technically, if you look at it, now actually I'm going to show you the graph of this one. So you can actually see what's happening. So we're going to look at between 0 and 3. And I want this to be there we go. That's better. All right. So we're looking at this problem from there on. But from there to basically there, x equals 3, this function is increasing and not decreasing. So can we do the integral test?
Yeah,
Why?
because you can change the limit. Change the bottom from 1 to 3. The integral.
Okay. We could. You don't actually have to, though. So, because if we did change it to 3, we would have to pull out those couple values anyway and add it to the front. So, by just doing that and pulling out those couple of values, I would then be able to do it. So, because the function in general is decreasing and it's not like increasing at any like random spots within it, I can do this. Because after 3, it is going to be decreasing from that point all the way to infinity. And I know that. So it is one of those one little catches in the integral test that you go, wait, that makes no sense, but it's a way out in all intents and purposes. Because the function is typically decreasing for the rest of the values, we can still use the integral test on this one to determine if it is convergent or divergent. So since I can now determine okay. We're going to do the integral test on this one to see if it converges or diverges. So I have ln of x over x dx. Okay. So how can I do my, what's the integral? Oh, sorry, from 1 to infinity.
So on those ones.
Oh. Then good. I already wrote the 1 to infinity there. All right. So find me the integral of that. Yeah, so we're going to have to use u substitution on this one. So u is ln of x. So du is. Hey, we have that. How about that? And if I plug in u of 1, that's 0. And u of infinity is still infinity. Of u, which is what? What's the integral of u? U squared over 2 from 0 to infinity. So this is going to go to infinity. So that means this series is divergent. So when I said the majority of your test is going to be just telling me if it's convergent or divergent, this is in essence what the majority of your test is going to be. Okay. Notice I just didn't look at the original problem and goes, that's divergent. We're good. Move on. I want to see the work to figure out why you determined it was divergent. If you don't show me the work, you don't get credit.
Not even like 3 points.
Not even anything. Because it's literally at that point, it was a guess that it's a 50-50 shot. So no. This is the one test that you can get the right answer, and if you don't show me your work, you'll get 0 points. All right. So the question comes up now is, how can we estimate the value of a function to a specific number of decimal places? So anytime you use a computer or a calculator to do a summation of a series to give you an actual answer, it is in essence doing what I'm about to show you. Okay, this is how the computer determines what it needs, how many it needs to add to give you the value that you want. Right? And depending on the function you put in, This is why sometimes your computer or your calculator takes a second to give you the answer, because some problems it's going to have to add a lot more values to give you a good estimate than other functions. Okay. So if you remember when we were looking at the integral at the beginning, I said the integral is the area under the curve, right? And I said that when we're looking at the sum or the series, it's going to have those little holes, correct? So the integral, if we take the integral after a certain number of values, that's always going to be a little bigger than what would actually be left over. Does that make sense? So I don't know if I have a picture right here. I do not. You can finish writing. I'll give you a second. I'll switch over in a minute because I have to find the picture anyway. All right. So here's my picture. So if we have some n value, doesn't matter where that n happens to be. So n could be 10, 12, 20, 30, whatever it happens to be, doesn't matter. Each of those blocks would be the sum of whatever was left over, all the way out to infinity, correct? If I took the integral, I'm going to have those blocks plus an ever decreasing little extra, right? So instead of trying to sit there and figure out all those extra blocks, I have a way to find my integral and find the actual answer of that integral. If I can find the actual answer of the integral, I know that my sum is within that area of the actual answer. Does that make sense? Yes? Good? Concept? So let's look at one and see how it works. All right. 1 over n to the third. Is it convergent?
Yeah.
Why?
Zero.
No.
P series.
It's a p series, and p is 3, and 3 is greater than 1. So this series convergent. Awesome. Great. Find me the first 10 terms. What are the first 10 terms?
1/3.
1 over. So the first term would be 1 over 1 to the third, right? So 1 over 1 to the third plus 1 over 2 to the third, 3 to the third, 1 over 4 to the third.
That's quite long.
10 terms. I don't know. You can do this. Good. I'll do it this way. All right. Go back to Desmos. Sum 1, and I wanted 10 terms, right? To the 10. And by the way, I got that literally by typing the word sum. It gives you that. So 1 over 10, and it's 1 over n to the third power, correct? That's giving me, that's the sum of the first 10 terms.
Total guy.
Okay. So that makes your life a little bit easier. You can use that to calculate those things out without having to do out every single one yourself. Which I don't think any of you would have actually done anyway.
So what does it convert to?
What?
Series.
What do you mean?
Does it go to?
But it depends. We know it converges. I don't know what it converges to. There is no way for me to calculate what it converges to. So what we're doing is we're going to approximate. The question is how good is that approximation? Okay. So we've now got that answer. That is adding up the first 10 terms. So 1 over 1, so basically 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125 plus all the way up to 1 over 1,000. We added all those terms up, and that's the answer we got. Okay? How accurate is that then? Now, that's where my integral test comes in. If I take the integral of all values from the 10th term on, that's going to give me the error that's left over. Or at least it's going to be a little bigger than the error that's left over. Okay, it's not going to give me the exact error, because if I can find the exact error, I'm good, I'd have the answer. But it's going to give me an estimate of what's going to be further on from that. So I'm going to look for the integral of 10 to infinity of 1 over x to the third. So what's the integral of 1 over x to the third? Remember, 1 over x to the third is the same thing as saying x to the negative third, right? So what's the integral of that? Negative x squared over 2, right? And we're doing that from 10 to, oh, negative 2, sorry. Infinity. So I'm looking at negative 1 over 2x squared. From 10 to infinity. If I plug in infinity, what do I get? 0. If I plug in 10, what do I get?
1 over 200.
Negative 1 over 200. So my error, my remainder, is less than or equal to 1 over 200, or 0.005. Yeah, it is. Because it's minus a negative. That's why I left it as 1 over 200. I didn't script my negative sign this time. So by adding up the first 10 terms, I have my answer to within 5,000ths of a place. So in actuality, this answer is accurate to within 2 decimal places. Okay. I don't know what my final answer is going to be, but I know my answer right now is going to be 1.19. I know that for a fact that it's going to be 1.19. After that point, those other numbers can change.
All you really need.
Okay. Well, it depends on how accurate you want your answer, or how accurate you want your information, or how accurate you need for your space station. Like, it's just a matter of what you're talking about, right?
Oh, yeah, that's
Remember, like the Hubble Space Telescope was off by less than the thickness of a human hair, and it was blind. Everything was blurry. They had to literally go spend $700 million to make glasses for the Hubble Space Telescope. It was kind of funny, but it was off because he was off by, I think it was 1 micrometer. Like, that was literally how much he was off by. So 6 decimal places out. That's how much he was off by, and it was enough to make the telescope worthless.
I'm pissed.
So, well, yeah, considering they sent it up into space before they figured it out. It was a big controversy in 1990 when they sent it up. And the lens was made in Danbury, Connecticut. No. So, but it just goes to, it's like, I use that example in my math classes of high school stuff because, like, it won't matter. I'm like, well, it cost us $700 million to fix that one mistake. Like, I would have liked that $700 million. Like, everybody would have. Like, So little mistakes can make a big difference. So depending on where we're asking it around to, that matters. In this case, we're off by 5 thousandths at the most. So the next question comes is, well, what happens if I want to know, I want it to be accurate to within 3 decimal places. So I want it to be accurate within 0.0005. How many terms would I need to add? There's no point in guessing. We can figure it out. So I know we have, actually, double this. We know that my integral, and we're going to say instead of 10, because I don't know which number I'm going to use, I'm going to put an n, is negative 1 over 2x squared and to that, which ends up equaling negative 1 over 2n squared, or positive 1 over 2n squared, which we did basically with this stuff down here anyway. So I want that to be greater than 0.0005 or equals 0. Oh, sorry, less than, not greater than, because I want it to be less than that. All right, so I want it to be less than or equal to that. So how do I solve this for n?
The reciprocal.
So 1 0.0005 times 2n squared. What's 2 times that?
What?
The 0.0005.
0.0001.
Almost.
0.0001.
Almost. You said the same thing twice.
0.001.
There you go.
My bad, it's a lot of zeros.
So now we can divide by the 0.001, which is 1,000. And how do I get rid of a square?
Square root.
So what's the square root of 1,000?
100.
Nope.
Sorry, 10.
Nope.
What?
10 times 10 is 100. 100 times 100 is 1,000.
You just said 100. 100 times 100 is 1,000.
Sorry, it's 10,000.
Um,
You guys all have calculators.
50.
50 times 50 is 2,500. You all have calculators.
Sorry, you're getting at.
17.3.
You've proven all the math teachers in the 80s and 90s wrong. You do have a calculator in your back pocket at all times. $31 point something. So I don't want the point something that would be less than, right? So n has to be 32. So I'd have to add up the first 32 terms to have my answer accurate within 3 decimal places. No, it's something backing up. So if I go 32 terms, I now have my answer as 1.201.
Got up a little point.
And the nice thing is with Desmos, like you can actually just put in the huge numbers here. So if I keep adding zeros, the actual answer, or very close, the actual answer is 1.202. So it's within that
the answer
third
was
decimal
32.
place.
Good.
So I would need to add the first 32 terms to get to be accurate within 3 decimal places.
All right.
Because that 5 is going to change the last digit. That's why that's the 3 decimal places. So we can't necessarily find the exact value. But by using the remainder theorem, we can find pretty close to the right answer. Okay. In this case, I got to add 32 terms to get to that right answer, to get to within 3 decimal places. But we're getting pretty close at that point. All right. So if we noticed, or if you didn't notice, that's okay. You'll notice that the R is between 2 values, right? I've only done this side because when we were looking at it, we just wanted to know how close that actual answer. Oh, you're right. I went on the screen. Thank you. So we've only looked at this side over here, the end value, because I just want to make sure my remainder was less than some certain number. However, this side says that my remainder is going to be greater than this number. It's going to actually be between these 2 numbers. So not only can I find out what my remainder is less than, I can find out what my remainder is between. So that was what was our, this is the change. If I add that sum that I got for those first 10 digits, or the 10 places, to both sides, I can get a range of where my actual value is. Okay? Which could be helpful. So if you remember, the first 10 terms was that. That's the first 10. So S10 equals that. So I'm going to have S10 plus the integral from 11 to infinity of 1 over x to the third dx. And then S10 plus the integral from 10 to infinity of 1 over x to the third dx.
That is quite a lot to write.
All right. What was the integral from 10 to infinity of 1 over x to the third dx? We just did that one.
At 1.19.
No, that's S10.
Sorry, for the 32.
Gotta repeat that. We're getting a little slow.
We did the integral from 10 to infinity, right? My answer was 1 over 200. So I know this side, it's 1 over 200. We also remember that that integral was 1 over 2n squared, right? So if I'm now plugging in 11 instead of 10, what's 11 squared times 2?
132.
242. 11 times 11 is 121, times 2 is 242.
Oh, yeah.
was it? Not 197531985 567. So if I just add those two together, I know my answer is between those two numbers. So it's somewhere between those two numbers. I don't know exactly where it is between those two numbers, but I know it's somewhere between those two numbers. So what would be the, if you were going to look for a number between those two numbers, what would be the easiest number for you to look for?
0.222.
Why?
Because I like it.
What would be the simplest number to find between any two numbers? Yeah, the average, the middle, right? So if we found the middle number of those two, the middle number is 1.202098102.
What is it? Oh,
And that's the number Desmos gives me when I added 10 billion, the first 10 billion places. Yeah. That's pretty darn close. So with the first 10, just adding up the first 10 digits using the integral remainder theorem, we can get an answer that's really, really close to the actual answer. Like we're within 4 10,000ths of a place. Tens, hundreds, thousands, 10,000. No, sorry, 400,000ths of the actual answer. That's pretty good. By just adding up the first 10 places and doing the remainder theorem, so we have those extra pieces added in there. That's how your computers do it. That's how your programs, that's how your calculator works. All right. Let's do a couple quick little problems. All right. You have 3 problems. I want you to write down on your paper 3 letters, C's and D's, for convergent, divergent.
nice and quick.
You got to tell it's got to be right.
I hear it. I hear it.
So here's the thing. You get all 3 of them correct, you're done. You can go home.
Ooh, I'm a killer.
If you don't get all three correct, you have another problem to do.
Is that we have-
Nope, I just want to see the C's and D's. So technically, yes, you have a 1 in 8 chance of getting it right. See you next week. I'm seeing my Thursday.
I got Nope. What? Alright.
Every one of these is a P series. What's the square root of 2? Approximately.
Less than 1.
Is it?
Yeah.
What's 1 times 1?
1.
Okay, what's 2 times 2?
4.
So it's got to be between 1 and 2.
Wow.
It's 1.414. It's got to be greater than 1, otherwise you get 1, not 2.
If the square root of 4 is 2.
Right.
That was half of that. Not less than
But the
4.
square root of 1 is 1. So if it's bigger than 1, the number's got to be bigger than 1. Forget the 4, it's got to be bigger than 1. So since it's bigger than 1, that's convergent. Negative 0.999999. It'd be 1 over that, right? Because it's negative. Is it greater than 1? No, it's less than 1. So that's divergent. 1 over 8, 1 over 27, 1 over 64. 2 to the third, 3 to the third, 4 to the third,
That's
5 to the third.
That's the original one you showed us.
That is n to the third. And at 3 is
Isn't that-
convergent.
Isn't that convergent?
Yeah.
So
So it's C, D, C. Convergent, divergent, convergent. All right, you got one problem there.
If I got them all right, can I go?
So the score on your paper is 10 points lower than what's on the actual grade.
Is that, it's.
Hmm? This one you got to prove to me though.
Oh, yeah.
And it's a P series. I'll tell you that much. All the scores are also on Blackboard, so you can easily look at your Blackboard grades too. What's the pattern?
They're all going up by 1.
Over n to the root n.
Right, 1 over n to the root n, right? So that's 1 over n times n to the 1/2, right? Which is 1 over n to the 3/2, right? So P is greater than 1, so converting. Not every P series problem is going to be as simple as n to the second, n to the third, n to the fourth. Some of them you have to think about. Okay. See you Thursday.